Okay, so with the administrative stuff out of the way, let's get back to the lectures. So today we're continuing on Étale groupoids, and specifically we want to talk about how you can form C-star algebras from Étale groupoids, and even certain kinds of twisted Étale groupoids. So if you just as a sort of quick recap, so remember last lecture we introduced groupoids. So they can be looked at in various ways, but basically they're like groups, except instead of a product everywhere for arbitrary pairs of elements, you only have a product on certain specific pairs of elements. And these specific pairs are usually denoted by G2. So this inclusion here can be strict. The product is not necessarily defined everywhere. And because of that, there can be many units, not just a single one, as in the case of groups. So equivalently, if you want a quick, dirty definition of a groupoid, and you're familiar already with category theory, then you can say that groupoids are basically categories of isomorphism. The key thing being that when we look at groupoids, we generally don't worry about objects. Usually the units, in a sense, take the place of objects. So yeah, I mean, it's well known that categories do have an equivalent object-free definition where the same applies, the units take place of objects, and this is usually more convenient when you're looking at groupoids. In particular, on any groupoid, you have these source and range maps, which are like the domain and codomain map of a category, right? In the case of groupoids, they have a kind of nice form, and that is that the source groupoid, the source unit of any element G, is just its inverse times G, and this product is always defined. And likewise, the range unit of any element G of your groupoid is just the unit you get by taking G times G inverse. Okay, and the topology on a groupoid is very important, particularly when we want to define certain C-star algebras from them. So remember, we defined a topology on G to be Étale if all those structure maps, the source map, the range map, the product where it's defined, and the inverse are all both open and continuous maps. So open, remember, means the forward image of an open set is open. Continuous means the inverse image of an open set is open. And both, you need both if you really want to do C-star algebra theory with these Étale groupoids. And a nice equivalent definition of being Étale actually is that it has a basis of open slices. So a slice, remember, of a groupoid is simply a subset on which the source and range maps are injected. They're one-to-one. Okay, and if it has a basis of open slices, which is also closed under taking pointwise products, where they're defined, and inverses, so they form an inverse semigroup in the natural operations. So if it has such a basis, then it's Étale. And conversely, if it's Étale, then the collection of all open slices forms a basis for your topology and is closed under the products and inverses. And we looked at a few simple examples. So any topological space is an Étale groupoid when you give it the trivial product, for example. So just where the only products that are well defined are the sort of identity products, x times x, in which case the answer is x. And at the other extreme, you can look at discrete groups. Remember, groups to be Étale, the only possible topology they can have are discrete because the only slices they have are the singleton slices. This is essentially the reason. But of course, there's sort of two extremes, and there's a lot of other more interesting examples which lie somewhere in between. So as one example, we gave what I call the car groupoid, and this just consists of infinite sequences, infinite strings of zeros and ones under the equivalence relation, which is tail equivalence. So you don't look at all pairs; you look at only those pairs for which they are equal beyond some point. And then these have a natural Étale basis, just consisting of all those pairs which start with some fixed t and some fixed s, and are exactly the same from that point on. And we showed, for example, that this is an Étale topology, but it's weaker than the other way around. It's stronger than the product topology. The product topology itself that you would usually consider is not Étale. So Étale, when you're dealing with Étale equivalence relations or Étale groupoids, you have to often be define the topology in a perhaps slightly different way than what you might be used to. So hopefully that's jogged everyone's memory about last week. So we also did kind of just start talking about how to define C-star algebras or algebras of functions on these Étale groupoids. So let's just sort of review what we were talking about at the very end last lesson. Let's take our Étale groupoid G and consider a couple of continuous functions on G. What you would like to do is again define the product by convolution. So remember a couple of lectures ago, we were looking at functions on finite groupoids. And then this turned out to be, first we did things in an operating theoretic way, but then we discovered that really we're just looking at functions from G to C under convolution. This was really the equivalent way of defining the product. But in this case here, where we have an Étale groupoid, which is not necessarily finite, it's not necessarily compact even, there's a couple of issues. So the first one being that the sum here may not be finite, so may not be well defined. As long as you have, I mean, you could also consider the even infinite sums, so long as those finite partial sums converge. But even that is not clear for two arbitrary continuous functions A and B, right? Okay. And even when they do converge, even when you can actually make this well defined, it's again not immediately clear, at least, that the result, the function AB you get, will also be continuous. Right? We want a C-star algebra. We want to be able to take continuous functions and multiply them in some way by convolution, and again get a continuous function, not just some other random function. So this is a bit of a problem. So to resolve these issues, what we really need to do is be a bit more restrictive about the kinds of functions we're dealing with. We can't deal with arbitrary continuous functions, at least not at the outset. So to define the kinds of functions we really want to focus on, we first define the notion of the support of some function. So the support is simply the collection of all groupoid elements which your function A does not map to 0. In particular, let us note the continuous slice-supported complex value functions by this S of G. So we're looking at continuous functions from G to the complex numbers, but such that the support is a slice, necessarily an open slice, right? Because A is continuous, so the support has to be open. So it has to be an open slice of G. And then we're in business, because with slice-supported functions, we know that this is actually well-defined. And moreover, that the resulting function you get from doing convolution here is again going to be continuous. So, and only one of the functions here has to be slice supported. The same would apply if B was slice supported and A was just continuous, right? But certainly if both are slice supported continuous functions, then again, this is well defined and AB is continuous. So proof, well, notice that I think this is sort of what we're getting towards at the end of last lecture. So notice that if you have some F here, which is an element of your groupoid, which is in not just the entire groupoid, but actually shares a range unit with some elements in the support of A, right? That's basically what they're saying. This set here is consisting of all those elements in G, F and G. So the range of F is the same as the range of some elements of the support of A. So in this case, you know that when you want to evaluate A, B, and F, right? You want to evaluate the sum here. Then there's actually, because A is slice supported, there's only one possibility for G here, right? And the only possibility for G here is that we take this T of F, right? The only possibility for G here is that we take G in the support of A, which has a range element in common with F, right? Because A is supported on a slice, there's only one possibility for that, right? Remember, the range map on any slice is injective. So there's only one possible choice of G we have. And if we want to write it down more precisely in some sense, it's really the element TF, where TF is what you get by first taking F, looking at its range, and then taking the inverse of the range map, but only the inverse restricted to the support of A. So this map will give you in the end, some element in the support of A, whose range is equal to the range of F. Okay. Because the range map here is continuous, and because the range restricted to sub A is also not just continuous, but an open map, then its inverse is also continuous. And so composition of continuous functions is continuous, therefore T is continuous. So this is really where you really need the fact that R is an open map, right? if this wasn't true, if it was just a topological groupoid, we wouldn't be able to do this. And so we wouldn't be able to do this in a continuous way anyway. Okay, so ABF is this multiple here where TF is uniquely defined like so. Okay, but again, okay, so well, firstly, it's well defined, right? This sum is going to be 0 everywhere except at one possible element of G and H, right? But also, it follows that the resulting function is continuous. Again, because we're just composing continuous functions, right? T is continuous, as we just mentioned, but composing T with A, that gives you a continuous function. Again, T of F is continuous, but the inverse map in your groupoid, that's continuous. The product in your groupoid, that's continuous, so this part is continuous. And then composing with B at the end, again, this is a continuous function. And I guess last but not least, the product on the complex numbers, right? That's definitely a continuous function as well, right? So the upshot being that this function you get in the end is indeed a continuous map, at least on the elements we've been looking at, right? At least on those elements in this subset that share a range with some element in the support of A. But you want to show it's continuous everywhere. So what about all those other points? Well, all those other points, we know that this sum, in fact, is going to be 0 at all those possibilities for G and H, that A and A of G will in fact be 0. And so the whole product will be 0 and all the sum will also be 0, right? Simply because if there's no element in the support of A, which shares a range with F, then all those G's here must lie outside the support, right? If it's outside the support, then by definition, A has to be 0 on that element, G. And that almost gets you what you want. The only problem being that the support is open, so the complement is closed. And while it's definitely continuous on the closure to be, well, what should I say? It's continuous when you restrict to the closure. So when you look at the closure as just a space in the relative topology, if you want to show it's continuous on the boundary, then you really have to find some slightly larger open set on which you can show it's continuous. But that's not too hard. I mean, basically the formal argument goes like so. You say take some small epsilon greater than 0, and notice that you do have some open set containing the complement here, containing this closed set here, right? On which A is always at most epsilon, right? It's 0 on this set, and therefore you can just widen it a little bit. And because A is continuous, that means you can't make A. You can enlarge the set without enlarging the modulus of A by very much. You can take an arbitrary epsilon greater than 0. And so in the end, because that is true, and then on this slightly larger set, right, A can have modulus epsilon, but at the same time, B is going to be bounded, right? So at least on this compact set, right? That's true. Maybe I needed compactness here. So I guess, yeah, maybe B here actually probably should be either compactly supported. Either A or B, I think, should be compactly supported, maybe to make this claim. Because sure, A may be small, but there is a slight problem here that B could sort of counteract that and get infinitely large in some sense. So I guess really B should be I get it, compactly supported, or even just bounded, right? Just need B to be bounded to ensure that this is true. So slight correction there. I'll try and correct that in the notes. So once you know this, well, you've shown it's continuous on this set. You've shown it's continuous on the complement of that set, or indeed an open set containing the complement. Therefore, it has to be continuous on the whole of your groupoid, and you're done. Right. Okay, so that's good. So we know that convolution is well defined, gives you a continuous map, as long as one of those functions is slice supported, and one of those is bound, and the other one is bounded, basically. Now let's generalize a little bit further and look at compactly supported continuous functions. So of course, the support itself is open, which means it's very rarely compact. However, you can always take the closure, right? So to say compactly supported, you're really saying that the closure of the support is compact. Okay, now we have a little proposition which essentially reduces the statement we're going to make about compactly supported guys to the result we had previously for slice supported guys. So as long as G is now locally compact and Hausdorff, this is going to be important now. So it's a locally compact Hausdorff Étale groupoid, then in fact, every compactly supported function on G, continuous compactly supported, is a finite sum of elements of SG, finite sum of slice supported elements on G, again continuous. So the proof is very simple. So as G is Étale, remember you have this nice basis of slice supported, no, sorry, not slice supported. You have this nice basis of open slices. In particular, we can cover the closure of the support of A, which is compact, by finitely many of them. Okay, this is just, the definition of compactness. Basically, you can at each point you have an open slice containing that point, so you can cover it with all these different open slices. But by compactness, you can replace that now with a finite subcover. And if it covers the closure, well, of course, it covers the support itself. Okay, and now we start using this local compactness and Hausdorffness. So it's a standard result that every locally compact Hausdorff space is, well, what I guess some people call paracompact. And I guess, regardless of whether you know what paracompact means, the point is, what we need here is that you have a partition of unity subordinate to this cover. So hopefully you're familiar with this terminology, but basically, if you have a space and you have some open sets covering your space, a partition of unity subordinate to that cover is simply a collection of functions with ranges in 0, 1, right? Such that their supports all lie, each one of those functions has a support which lies in one of those open sets. And moreover, when you take the sum over all of them, you always get 1, right? So that's why it's sort of a partition of unity in some sense. Okay, so we have our cover of the closure of the support of A, and we can cover the whole of G then, if you like, by just adding in the complement. And then we get this partition of unity. And in particular, what this means, as I said, is that you have these functions, Z1 to Zn, some finite collection of functions, because it's a finite cover of open sets, who each have support in this open cover. And these open sets are, in particular, slices. So that means these functions will be complex valued functions with slice supports. Hang on a second, I'm just going to close the window. Okay. And because they sum to 1, and together with this, there's going to be one function, I guess, which is supported on this guy. And so that means they'll sum to 1 everywhere. But if we remove the function which is supported in this set here, then they won't sum to 1 everywhere. However, they will sum to 1 everywhere on the support of A. And that's all we really care about. And that means that we can write A as this sum of finitely many functions, each of which is supported on some slice. And the product here is not any kind of convolution product here. This is just pointwise, right? So I'm just saying at every point X, look at the value of ZK of X and multiply that by the value of AK at X, from any X in your groupoid. So we expressed it, and because these are supported on some open slice, well, then the product is definitely also supported on an open slice. If this is 0, then the product is 0, right? Okay, so we have this nice collection of finite functions, and that's it, right? These are exactly the finite collection of elements of SG that you needed to sum to your element A. Okay. So as a corollary, it follows that whenever you have some compactly supported continuous function now, and some other continuous function, which again I think should really be bounded, then the product is well defined and also a continuous function on G and given by convolution. Right, because the idea being that, okay, you've got your A, you could split up A into finitely many functions of this form here, right? And we know that when we take each function individually and take the convolution with B, then that gives us a continuous function well defined by the previous result. Okay, but then there's finitely many of those which sum to A. So if it's true for each individually, then sum them up. Again, you have a continuous function. That's basically it. And this allows us to now look at the reduced C-star algebra of an Étale groupoid. So for any locally compact Hausdorff space, we define this reduced C-star algebra. Well, we first define this star algebra C of G using convolution. Right, the fact that this is well defined was just on the previous slide. So remember, I said B had to be bounded, but if B is in particular compactly supported, then it has to be bounded. Okay, and as before, we can now define on this star algebra, we can define this 2 norm using convolution. So that's, yeah, it's kind of like with groups, except now we just take the supremum over all units of this A star A. So the square root of A star A X. And then to get the B norm, we basically look at it as if it's an operator, like it's operating on these compactly supported functions. So we look at the supremum of the 2 norm of AB for all those B's in the 2 unit ball. Exactly like we did before with, finite groups, essentially. Okay, and the reduced C-star algebra is by definition the completion with respect to this B norm of the compactly supported code. With finite groups, remember, we didn't have to take the completion. It was already complete because any finite dimensional norm space is automatically complete. But if we're dealing now with infinite G, non-compact G in particular, then this norm is definitely not in general going to be complete. But it's not an issue, or it's not a major issue because you can always just take the standard completion to get you the C-star algebra. And this includes already some, the most basic example of a C-star algebra. Specifically, if we have a locally compact Hausdorff space, then we can always consider it as an Étale groupoid with this trivial product, which I mentioned before. And in this case, the reduced C-star algebra is exactly the C-star algebra of functions, complex valued functions, continuous, vanishing at infinity. So this is just a fairly standard result that any function vanishing in infinity here can be approximated arbitrarily closely by these compactly supported guys. I mean, the idea being that if the function vanishes in infinity, then outside some compact sets, you can basically, adjust the function a tiny bit and make it go down to 0 very quickly. And then with that won't change the function so much. And by doing that on larger and larger compact sets, you will approach the original function you started with, which vanishes at infinity. So it includes all commutative C-star algebras, this reduced C-star algebra construction, right? Just for trivial groupoids. On the other hand, it also includes all groupoids you obtain from finite groupoids, even compact groupoids, right? Then again, you don't need to take the completion even, that these continuous functions are already complete. Like if G is compact, then C of G is just C of G, right? That's a median. And the fact that they're compact means that, well, with a little bit of extra work, you can show that it's already complete. Right? If it's finite, that's trivial. If it's compact, I guess you would have to do a bit more work to show that, we'll talk about this more later, in fact, like why when it's compact, then it's already going to be complete. We'll see that later on. Okay, so as I was saying, so this means the reduced groupoid C-star algebras include all the commutative C-star algebras, but also all the finite dimensional C-star algebras. So remember, one of the sort of motivating reasons for considering groupoids over groups was that even in the finite case, the finite group C-star algebras, they don't include your basic example, which is Mn, right? These matrix algebras. But if you move to finite groupoids, then there is a very canonical groupoid equivalence relation even, which will give you the C-star algebra Mn, this matrix algebras. Okay, and this includes all finite groupoids, just their Étale with a discrete topology. This allows you to look at the reduced groupoid C-star algebra. And so therefore it includes all, by Wedderburn's theorem, it includes all the finite dimensional C-star algebras. They're just direct sums of these matrix algebras, which come from disjoint unions of groupoids formed from equivalence relations, essentially. And a general fact, which is maybe a little bold to say, is that pretty much all natural C-star algebras, natural in some sense, can be defined from groupoids in some way. And often there's many ways, right? There's no result saying that the groupoid, the Étale groupoid associated to some C-star algebra is unique. It's not like with topological spaces and commutative C-star algebras, right? If you look at commutative C-star algebras, there is indeed a unique locally compact Hausdorff space, such that your C-star algebra is just C0x for that space X. But with groupoids, that's no longer true, at least not without some further restrictions on the kinds of groupoids you're looking at and the kinds of C-star algebras you're looking at. This leads into Kuhn-Jarvano's file groupoid construction, but again, we will probably talk about that maybe next lecture or the lecture after. Because the most naturally occurring C-stars are defined from groupoids. Maybe not the reduced groupoid C-star algebra, but either this or the maximal, or maybe in some cases something in between. So, for example, this non-trivial groupoid that we define, this car groupoid, does indeed give you a very natural, well-known C-star algebra known as the car algebra. And the normal way to define it is really just as an infinite tensor product of 2x2 matrices, or sometimes as, or sort of equivalently as what you would get by taking a direct limit of matrix algebras where you embed M2 in M4 by just sort of copying it twice along the diagonal, and then likewise M4 you embed in M8, et cetera, and you look at the direct limit of that, and this gives you this car algebra. But there's also, I think, maybe a nicer way of looking at it as a groupoid C-star algebra when you just take this G to be your car groupoid. If you're interested, incidentally, car here stands for canonical anti-commutation relations. So yet another way of defining the car algebra is basically as a kind of universal C-star algebra generated with certain generators satisfying these canonical anti-commutation relations. But we won't get into that. Apparently, this is how they sort of naturally arise in some kind of physics context. But yeah, we're just into the abstract C-star algebra theory, so we won't worry about that. And before we move on, I mean, the reduced C-star algebra is sort of my preferred way of defining a C-star algebra from a tile groupoid, but I would be remiss if I also did not mention another very standard way of doing this, and that is to look at the maximal C-star algebra. So you start off in exactly the same way by looking at this star algebra of compactly supported continuous functions on G. But then you note that this norm that we had before, the B norm, is not in fact the only C-star norm you could put on this star algebra. There can be many, and in particular there is another sort of canonical choice, and that is to take the maximal C-star norm on CC of G. So it's just the supremum of the norm. So for any particular, it's the supremum of A where A is any C-star norm on CC of G. And so because you can check that this will also give you a C-star norm, so the supremum is really a maximum. What is not clear, I guess, at first is whether this is finite, right? Like you might think at first that, oh, I have a particular element A, maybe I can define larger and larger C-star norms, and so when I take the supremum, maybe this will actually be infinity. But that does not happen, and to see why, let us just prove a couple of little results. So first, take a C-star norm on the complexly supported continuous functions on G, and take some, let's say, slice supported or compact slice supported function on G. So the claim here is that any such norm, in fact, has to be bounded by the usual infinity norm. And because it's slice supported, the infinity norm, the 2 norm, the B norm, these all agree. You can check that. It's not too hard. So we'll first note that any C-star norm on this subalgebra here, where you look at compactly supported guys on G0, I mean, which I guess I'm really identifying these with the functions on G, which are supported on some compact subset of G0, the unit space here. So this is not the whole of CC of G. I'm only looking at the sort of diagonal part, right, if you like, of this. So first, any C-star norm extends to the unitization in some sense, just the algebra you get by just adding in all scalar multiples of 1. So 1 here being the function which is just 1 everywhere constant on the unit space G0. And this is essentially the same, to show this is essentially the same as what Karen was doing before when you have a C-star algebra and you want to unitize it, right? exactly the same sort of construction or the same definition of a norm will then get you this will then get you a norm on this larger C star algebra, which extends the original norm on CC of G0. And once you know that, things are much easier because you say, well, let's take some positive continuous function which has compact support in the unit space. And notice that okay, that means that A has to be below this a scalar multiple of 1, where the scalar in this case is just the infinity norm of A. So it's below pointwise, but it's also below in the usual ordering you have on positive or even self-adjoint elements in a C star algebra, or in this case just a star algebra. We haven't got a C star algebra yet, just a star algebra, but we still can say that this is below that, in the sense that if I look at the difference here, this is positive. Positive in the sense that it has some self-adjoint square root, right? It's of the form A star A, right? For some, it's of the form, I should say, B star B for some B. In particular, it's of the form B squared for some self-adjoint B, right? Because if this is pointwise, this is a positive element, so it's always taking values in between 0 and the infinity norm of A. Well, if you take 1 minus that, then again, these are always positive valued. So you can just take the square root pointwise to get you this self-adjoint square root. Okay, so if that's below that, well, that means that, again, in C star algebras, we always know that if you have a positive element, which is below another positive element, well, then the norm of that element, again, has to be below the norm of the other positive element. And the norm of 1 in any C star algebra or any star algebra even is always just 1. So this is a scalar. You can take it out the front, and this norm of 1 just disappears, and you're left with the infinity norm of A. Right? So I guess you're maybe familiar with this in C star algebras, but it also applies to star algebras, right? Because you could always just take the star algebra with the norm and just say complete it to embed it in the C star algebra. That won't change the norm. And so that's the first step. So this works for the function supported on G0. Now let's look at some arbitrary function which is supported on some compact slice of G. Well, because it's supported on a slice, if you look at the product of A star A, the convolution product, then this in fact lies in the unit space, right? Because if you think about, the support, I should say, lies in the unit space. If you think about any element G for which this is non-zero, well, there's only two possible. What's the thing? Yeah, there's only one way of writing it as a product. One in the slice support of A, and another in the slice support of A star, which is the inverse of the support of A, right? So I guess it also goes back to this point that if you have a slice, O say, then if you look at O times O inverse, this always lies in the unit space. Likewise, O inverse O always lies in the unit space. So similarly, if you're taking the convolution product of things which are supported on slices, like A star A, then this again has support lying in the unit space. So then we can apply what we just worked out. So we know that the norm of A is the square root of the norm of A star A because it's a C star norm, but we know this is supported in the unit space. So this is in fact below just the usual infinity norm of A star A. Okay, but again, these are just complex valued functions on the unit space. A star A is just basically pointwise taking the value at A and its complex conjugate, multiplying them together, and that is that is by definition, if you take the square root, that is by definition the modulus at that point. So therefore, this just gives you the infinity norm of A. Yeah. So the upshot being that thanks to this, right, we know that this maximal norm A here is well defined or finite at least for arbitrary compactly supported guys. Again, using this result we had before. So this is again using the fact that we can write A as a finite sum of slice supported guys, right? And if all those slice supported elements are finite, they have some finite max norm, well then the max norm of A, it's subadditive, so it has to be less than the sum of all those individual max norms of those slice supported elements. And so it's, this gives you a finite norm, and so you can again then complete it to get your C star algebra, the maximal C star algebra of G. And I guess as a little corollary of the above result is that at least when A itself is slice supported, we already know what the maximal norm is. It has to be exactly the same as the B norm. It has to be greater than or equal to the B norm, right? Because this is a supremum. In particular, we could take the B norm as one of these C star norms on C star G. So it definitely has to be greater than or equal to B norm. But here we showed that if A is slice supported, it also has to be below the B norm. So it has to be exactly the same. It's only when you start taking sums of slice supported elements that you are not 100% sure what the norm is. It could be strictly greater than the B norm. However, it will still be finite. So this is pretty much it. This is how you define both the reduced and maximal C-star algebra of an Étale groupoid. But there are a couple of niggling little issues that you might be aware of. So the first issue is that the way we've defined the reduced groupoid C-star algebra and the maximal groupoid C-star algebra, we define them as abstract completions. So I guess if you're doing things more concretely, you would take, Cauchy sequences and look at equivalence, classes of Cauchy sequences and things like this, right? Or maybe there are other ways of abstractly defining this completion. But what is clear is that they are no longer, these elements in the completion are no longer just continuous functions. They're limits of continuous functions, sure, but they're not continuous functions themselves, at least not under. We don't know what the product is, right? The product is again defined by this limit, but we don't know that even if we could represent them as continuous functions, whether the product in the C-star algebra would be the same as the corresponding convolution of the functions. Would the convolution even be well defined? Would the sums converge? We don't know at this stage from the way we've defined these things. And indeed, for the maximal groupoid C-star algebra, this is in some sense unavoidable. You just have to deal with the fact that arbitrary elements are limits of compactly supported elements. They don't themselves necessarily have strict correspond. They don't strictly correspond to some actual function on G. With the reduced groupoid C-star algebra, you do have at least some hope of really representing these as concrete functions. But you have to do more work, or you have to define the groupoid C-star algebra in a slightly different, perhaps slightly smarter or neater way. This is what we will do eventually, I think, next lesson. But another issue before we get to that is that sometimes you want to be able to twist your groupoid in a certain way. And this particularly comes into play when you want to have some kind of generalization of the Gelfand representation. The Kumja-Renaud have this very important Weyl groupoid construction, and the idea is that you start with some C-star algebra, some nice Cartan subalgebra, and from that you define a certain groupoid. However, the groupoid that they define is not, strictly speaking, just a groupoid. It comes with a certain twist. If you want to recover the C-star algebra you originally started with, you have to somehow incorporate the twist in your construction of the C-star algebra. Okay, and so this is something we haven't looked at or haven't seen yet. This is somehow indicates that our reduced groupoid C-star algebra construction is perhaps not quite general enough. But maybe there's some extra structure we should include. And indeed, sometimes you want to include not just a twist, but maybe even some kind of bundle structure. So you might want to look at sections of a bundle of C-star algebras, or a bundle of Banach spaces over the Étale groupoid, which in some sense behaves as if it were a bundle of C-star algebras. More precisely, these are called Fell bundles over Étale groupoids. And these arise particularly naturally when you're dealing with cross products or even partial cross products. And so these again show that our construction is not perhaps as general as you would like to be able to include a number of examples in the literature. So what to do? Well, firstly, before I launch into the discussion of Fell bundles, this is something I want to do next time. I thought it would be good to give you an example of this kind of phenomenon. So what kind of twisting happens? What kind of twisted C-star algebras do there exist? Right? So before to introduce probably my favorite example of a twisted groupoid C-star algebra, I first want to just recall the notion of a projective space. Yeah. So So the n-dimensional complex projective space, hopefully you've met this at some point, perhaps in an algebraic topology class or something like this. But if not, it's fine. We're going to define it. So n-dimensional complex projective space consists of all one-dimensional subspaces of n+1 dimensional complex space. Right? So every one-dimensional subspace, remember, is generated by a single non-zero vector. So this is exactly what this is saying. And these come equipped with a topology, and there's various different ways you could define the topology. But the basic idea is that, yeah, if you imagine these subspaces as somehow, lines lying in the plane, then if the lines are kind of close, then they should be close in some kind of topological sense. If you want to be more precise about this, what you're really doing is you're looking at these subspaces, deleting 0, otherwise things would trivialize. So you delete the 0 point. So I've got 0, 0 here, but this should be the 0 of Cn+1, not just C2, right? So delete that. This should be the 0 of Cn+1. So you delete that point, and then you take the quotient topology. So where a set is open, if and only if, when you look at all the union of all the sort of equivalence classes that you get, that this is also an open set. But actually, there's what I think for a C-star algebraist, at least, a slightly nicer way of defining this topology, which makes it clear it's actually coming from a very natural metric. So first note that every one-dimensional subspace corresponds to a projection. So the projection here, corresponding to the subspace generated by V here, is what you would get, what you might recognize from linear algebra with Hilbert spaces. So to project W onto V, or onto the subspace spanned by V, you simply take the inner product with its conjugate, where the complex conjugate is done pointwise, right? And then just multiply by V. So this is your scalar, just multiply that by V. This gives you the sort of closest point in the subspace to the original vector W. So as long as V has norm 1, I should say. Otherwise, you would have to mod out by the norm here squared. Okay, and the dot here is the usual dot product, right? So if you conjugate first, then this is the usual Hilbert space product. But the dot product is a bit more convenient to use at this point, or at least it will be in a few slides' time. So once you realize that one-dimensional subspaces come from projections, well, okay, then the topology is sort of immediate. Just define the topology define the distance between two subspaces as just the norm of the difference of the two projection operators. Okay, that defines a metric on your subspaces, and then you look at the usual metric topology, right, with open balls. If you're looking specifically at the complex projective line here, so CP1, then this is actually homeomorphic to the Riemann sphere. At least the Riemann sphere looked at in a certain way as the one-point compactification of the complex numbers. Right? So basically take the complex plane and just add a point in infinity, sort of where the points going out to infinity converge in fact to this extra point you've added in. And you can be explicit and say, well, the homeomorphism is given by taking each complex number just to the subspace spanned by 1z, and the point infinity to the subspace spanned by 0, 1. So this gives you a nice homeomorphism. In the particular case, you're dealing with the complex projective line. So we know what the n-dimensional complex projective space is. Now we want to extend this in a very simple way to form a slightly non-trivial groupoid. Right? CPN, of course, forms a groupoid just with the absolutely trivial product, where you only multiply identical one-dimensional subspace. But this also forms a groupoid in the sort of in the usual way, where you look at pairs, arbitrary 0-1 pairs, and you can multiply them if the middle parts of the pair agree, and the answer is equal to the outer parts of the two pairs. Okay. So more explicitly, this is given like so, right? This is just the standard way of forming a groupoid from a Cartesian product of two other groupoids, right? And the inverse again, so V inverse leaves V unchanged, but it just switches the order of J and K, where J and K are just within 0, 1. So note first that this is compact, in fact. So compact Étale groupoids are not so common, but this is one of them. So this is a compact Hausdorff groupoid, just in the usual product topology. So again, often when you're defining Étale groupoids, you want something stronger or a bit different from the product topology. But in this particular case, we're actually quite happy with the product topology. So it's compact, right? Because CPN is compact, and this is just really 4 copies of CPN. Okay, and in this case, well, the product topology has this nice basis, right, where you look at some open subset of CPN, where you just fix the other 2 coordinates J and K, and these are in particular going to be open slices, and therefore the topology they generate, which in this case is the product topology, is indeed Étale, and they're also closed under products and inverses. It's easy to verify. We have our nice Étale groupoid, which extends just the trivial, the space CPN. Okay, and now note that if you look at what happens when you take the convolution product, because we're dealing with a compact space, CC of G is in fact already the entirety of CG, right? So we can define convolution on the entirety of CG now. If you look at the value at some fixed point of your groupoid, Bjk, well, then it's really just a sum of two products here, right? You can either put 0 in the middle here, or you can put 1 in the middle here. They're the only 2 options. And you'll recognize this as basically the definition of the matrix product of M2. You can always identify these functions on G with, in fact, M2 valued functions on just the CPN part. So specifically, you define, if you've got some function A on the groupoid, then you define a new function A. Maybe you should denote this by A prime or something. But you define a new function where it's a matrix now, where the matrix is determined by the extra values, the extra possible values of A at V. So V00, V01, 1011. Okay. And this expression here tells you that convolution of A and B does indeed just correspond to pointwise matrix multiplication. And this is sometimes a better way of, or an easier way of looking at things. Okay, so that's easy. This is in a sense, I guess, just a rather complicated way of defining this algebra here, continuous functions from CPN to M2. But I wanted to phrase it this way because there's now a way I can kind of twist this to get something a little bit more interesting. I can get what I'm going to call these Peterson C-star algebras. So to define these, let's define PPN to consist of all those continuous functions, again, on the same groupoid, right? CPN times 01 times 01, where those 2 coordinates at V00 and V11 are always just complex numbers, just like before, right? Easy. But we make a slight change where we define these sort of off-diagonal terms or off-diagonal entries of the matrix at the point V to not be complex numbers, but to be actual elements of the subspace V, right? So these are one-dimensional subspaces, but there's no canonical unit in any sense, right? You can always take any particular vector in V and note that that AV has to be some complex number times that fixed vector, but there's no real canonical choice for the vector generating V in this case. So we define the off-diagonal term to lie within V, and likewise we want the other off-diagonal term. We want its conjugate now, its complex conjugate, to be within V. Or we equivalently want A to be in the conjugate vector space, if you like. We can again consider every function now in this PPN as basically a matrix at each point of the projective space. The only difference now being that these off-diagonal terms are vectors, not complex numbers anymore. Right. And now we're going to define the products in the way you would expect, except now we have vectors, so we can't just multiply vectors. We have to use the dot product. We have to specify what kind of product we're using. And in this case, it's again just the dot product. Okay. And you can do some fairly elementary calculations to show that this is again, an associative product, and it distributes over addition, everything you would like. And that the conjugate transpose, which you obtain by just taking the the conjugate and then taking the conjugate and then flipping B prime C prime, that this again gives you exactly the kind of star algebra structure you want, together with the supremum norm, right? The supremum norm at each point, where at each point you're looking at the norm of the matrix here, where the norm of the matrix is just obtained by replacing B and C with their two norms, right? Like just considered as a finite sequence of complex numbers, you just look at the usual Hilbert space norm. Okay, so this indeed forms a C star algebra. Okay, this is not too hard to show. You can look at, they were first defined really in this paper of 71 by Peterson and Peterson, if I'm saying that right. But the question is, I guess, at this point, have I actually done anything, or did Peterson actually do anything? Was this rather complicated way of looking at bundles looking at vectors in the off-diagonal terms? Did this really give me a new C star algebra, or did this just give me a more complicated way of defining the C star algebra I already had, continuous functions from projective space to M2? Well, even though they're not in these off-diagonal terms here, are not complex numbers, right? When you're looking at elements of this Peterson algebra, they do still lie in a one-dimensional vector space. Right? And so the sort of obvious way you would define an isomorphism from which one? From here to here, is you would say, well, let's look for some function, some continuous function from n-dimensional complex projective space to just the two Cn plus one. Well, two these vectors which lie within that particular one-dimensional subspace, right? So you sort of just make a choice, basically, but you want to try and make some kind of continuous choice. And once you've made a continuous choice with this vector valued function v here, then for any a, which is just a continuous function to M2, you just use the off-diagonal terms as the scalar multiples to this continuous selection, if you like, little v. If you could do that, then indeed they would be absolutely isomorphic. But the problem is that there is no such function v. There's a topological construction, a well-known topological construction, which is due to Borsuk and Ulam. So to describe this a little bit more precisely, note that if we did have such a function v, then this would enable us to define a function on the 2n+1 sphere, right? When we view that sphere, this is a topological space, which could be viewed in many ways, but in particular, you can view this as n+1 tuples of complex numbers which have norm 1. So this will give you the 2n+1 sphere, and we can define a map on that by simply look at your vector x, look at the one-dimensional subspace it generates, then apply v to get you some elements of Cn+1 here, which lies in the one-dimensional subspace v, and note that, well, okay, this has to be a scalar multiple of x. So just define f of x to be that unique scalar multiple. This is, I guess, a sort of indirect definition, but you can see that the f here is uniquely defined. V maps onto the one-dimensional subspace spanned by x, right? So there has to be a unique scalar making this true. And this would give you a continuous function to S1, right? Just complex numbers of modulus 1, which moreover satisfies this extra condition that f of negative x goes to negative f of x, right? Because if you put in a negative x here and a negative x here, well, this doesn't change the subspace it generates, right? So v of that would be exactly the same. The only way that would be possible is if f of negative x is the negative of f of x. Put in other terms, it's basically saying this map f here takes antipodal points of one sphere onto antipodal points of another smaller sphere, namely S1. And Borsuk-Ulam theorem precisely says that this is not possible. You can't get a map taking a continuous map, taking antipodal points to antipodal points from one sphere to a smaller dimensional sphere. That never exists. So your function v here just doesn't exist. So what does this tell you? Well, it tells you there's no obvious isomorphism between these two things here. Nevertheless, you might wonder, well, maybe we just weren't smart enough. Maybe there's actually a more complicated kind of isomorphism, which doesn't just come from some vector value map V, but where you have to somehow map, a matrix at a certain point here to some kind of unitary conjugation, if you like, of the matrix you started with, or you choose the vectors in a smart way. I mean, who knows how you would actually do this, but this is only showing that the obvious way of defining the homomorphism or the isomorphism does not exist. Maybe a smarter way of defining it does. Right, so this is the question. But if we, again, be a bit smarter, we can show that, in fact, no, even this is not possible, at least if n is greater than or equal to 2. Right? So, and we can base this on this simple lemma that as long as you're dealing with n greater than or equal to 2, I can find some elements in my Peterson algebra, so a continuous function, right, which is diagonal, right, for which the off-diagonal terms are 0, they're the 0 vectors. At some point, certainly not every point, but at least one point of n-dimensional complex projective space. And the proof is, again, basically the Borsig-Ulam theorem, except now instead of just one function to just the unit circle, I guess, instead of just one function, now you have two functions, right? Okay, so we have two functions to c squared, like so. It's just we're using these two off-diagonal terms now, 0, 1, and 1, 0. And again, they map n-dividal points to n-dividal points, right? And if the matrix A here was never diagonal, then this in particular, this map here would never be 0. And so by simply dividing out by the norm here, then we would get a map from the 2n+1 sphere to the 3 sphere now, right? Because there's two copies of the complex numbers. So if you look at the ones with norm 1, this gives you the 3 sphere. Okay, but okay, it maps n-dividal points to n-dividal points. As long as n is greater than or equal to 2, this will be a higher dimensional sphere, which again contradicts the Borsig-Ulam theorem. Okay, so all of these guys here, they have to be diagonal at some point, right? And how does that help us? Well, in particular, what that tells us is that I can never have a partial isometry in my Peterson algebra, such that if I look at the sort of the range projection of A, and I sum with the initial projection of A, then I get the unit element of my algebra. So this never happens in this particular algebra. Why? Well, take some A. Notice that from our previous result, A has to be diagonal at some point, and therefore, as A is a partial isometry, right, then the only diagonal partial isometries consist of two complex numbers in the top left and top right, which are both in the unit circle. They're both just complex numbers of modulus 1, or possibly 0, right? But no, there's no other choices for A at that particular point, V. Okay, so it follows that then just by looking at the range, in this case, in either of these cases, A and A star are actually the same thing, right? So when you multiply themselves by themselves, you won't change anything. But because you're taking the sum here, these two elements here, you've got an element times its complex conjugate, which is just 1, and then you're taking the sum. So that gives you 2, either in the top left or the bottom right, or in both. But in any of these cases, this is definitely not the unit of M2. So the sum certainly can't be the unit element of the Peterson algebra. The unit element of PPN is just going to be the unit matrix, right, at every single point of complex projective n space. So there's no such partial isometry, right? And that really gives it to you, because if you just quickly note that if I look at my continuous functions from projective space to M2, there is a very, very easy way of defining a partial isometry which does satisfy this condition I just mentioned. Just look at the function which has entry 1 in the top right corner or the top left corner, doesn't matter, everywhere for all V, right? It's just constant. Then at each point you look at A star A plus A star A star plus A star A. You always get the identity matrix in M2. So there's a clear, a simple, algebraic property which this algebra has, which PPN does not. Okay, so great. So this this sort of complicated work we did, where we looked at vector valued functions, at least in the off diagonal terms, really did give us some new C-star algebra that we did not have before, at least when n is greater than or equal to 2. You might be wondering about the n equals 1 case, and this is a little bit trickier, but there is a way of doing it in a slightly more cohomological way. Use some basic check cohomology to prove that, again, these two things are not isomorphic, which is actually a bit more powerful because it tells you something perhaps even more interesting, that this PP1 here can't even be a corner of continuous functions from CPN to perhaps some larger matrix algebra Mn. Right? You can imagine that by looking at some algebra consisting of functions in Mn for some much larger n, and then cutting down by some kind of twisted projection, that maybe that would be able to give you PP1. But even that is not possible via this cohomological argument. And so, in a sense, this is some work I did with Farah in 2013. In a sense, what this really indicates is that the PP1, at least, is intrinsically twisted. Like, there really is no way of untwisting it in any kind of reasonable way and then cutting down by a projection. This just does not happen. So you really need the bundles here that you use to define them, or the vectors you use to define them in this sense, really are basically necessary. They're somehow intrinsic to the C-star algebra. There we go. So I guess I'm going to finish a little early today, but there's just one more thing I wanted to talk about. So that's one example of twisting, but there's another common way of twisting a groupoid, and that's by using a 2 cocycle. So say you have some function on G, or at least on pairs of G that can be multiplied to the unit circle, complex functions of modulus 1. And it's a 2 cocycle if it satisfies this specific identity here for any FGH, such that FGH is actually a well-defined product, together with these this sort of non-triviality condition that sigma RGG and sigma GSG have to be equal to 1. So if you have such a 2 cocycle, then you can define a kind of twisted convolution now. So again, you're looking now at just the usual complex valued functions on your Étale groupoid. But instead of just taking the sum of these products, you add in this little extra factor, sigma GH. And that defines this sort of twisted convolution. And the first thing to really check is that this actually still gives you a kind of associative operation. And this is really where this defining property here comes into play. So if you consider what you would get at some point E of your groupoid, if you first multiply AB by convolution, by sigma convolution, and then multiplied by C on the end by sigma convolution, you would first get this sigma FG appearing in the beginning, and then once you do the second step, you'd get this sigma FG comma H appearing in the second position. Whereas if you do other things the other way around, you would first get sigma GH appearing here on the right, and then at the end you would get this sigma FGH appearing here. But because the product of this and this is exactly the same as the product of this and this, by this thing up here, these two sums are going to be exactly the same, as long as the sums are well defined. So I guess I haven't stated it here, but yeah, assuming the sum is finite, let's say. Yeah. So again, you can then use this to define an actual product which is well defined and continuous everywhere on the compactly supported guides. So this will not always be defined for arbitrary A, B, and CG. However, it will be defined and will again give you a continuous compactly supported element as long as your A and B were already continuous and compactly supported. And there is indeed a way of looking at even these kinds of twists, these two cocycles. You can again use those to define a kind of bundle, and then look at the sections of your bundle as a C-star algebra. So where you're looking at things which might have vector values right? But there was a product defined in a particular way between the fibers of your bundle. And this is kind of like how we had before with, different vectors in one-dimensional subspaces, but you look at their dot products, right? So you can again use these two co-cycles in a sort of similar way to find bundles to again get something similar to what we had before with the Peterson C-star algebra. So that's really what I want to talk about next week. So next week, we're going to, my plan at least is to start with defining a Fell bundle, a very general kind of object. It's like you have an Étale groupoid, but over the Étale groupoid, you have these extra fibers and you have products between the fibers which make everything work. And then you can define a general reduced and also maximal Fell bundle C-star algebra by looking at continuous compactly supported sections and taking either the closure in an appropriate space or the completion. And this gives you a very general way of defining C-star algebras, which will be, as I said, it will give you pretty much all natural examples of C-star algebras that you could possibly imagine. And yeah, I guess I am finishing a bit early, but really I didn't want to have to start on Fell bundles and stop halfway through. So I think it's really best to stop now and really start again with the Fell bundles next week. So thanks again for your attention. Are there any questions? Oh yes, we have something in the chat here. Let me see. Do you upload the size of the course webpage? I don't think I have for the past couple of weeks, but yes, I should do that. I will. I think it. I think the slides from maybe the first lesson are there, but yeah, I'll make sure they're up to date either tomorrow or the day after. So yes. Any other questions? Yeah, maybe so. Yeah, maybe I should just go back again to the very beginning, just about our mini workshop. Okay. So any questions about the mini workshop too? Is everything clear? It looks like everything's good. Yeah, well, thank you again for your attention, and I will see you next week, hopefully.